My name is Doretha Cross, and I will be delivering the Vermilion Creek Watershed Water Quality Assessment Report. The first thing I want to talk about is the importance of learning SWOT and studying watersheds such as Vermilion Creek. This can be summarized in the following statement. The Great Plains streams and ecosystems, an integral part of the diminishing North American unpolluted fresh water supply that once encompassed 160 million hectares, have been continually degraded by urbanization and agricultural operations. In northeast Kansas, stream, lake, and reservoir sedimentation is a prevailing water concern. A major source of non-point source pollution is rainfall runoff initiated from agricultural fields. While many practices have been implemented in agricultural areas to mitigate the pollution and stream degradation, determining the current state or baseline is crucial in understanding potential future changes of water quality in agricultural production in Kansas impacted either by climate change or anthropogenic activity. Watershed residents in general are concerned about the availability and sustainability of resources for current and future generations. Those residents who reside and manage farmland within their watersheds have the greatest potential to mitigate polluted runoff through changes in land management practices. In this Watershed Water Quality Assessment Report, I will first talk about the watershed, giving a brief description of its location. I will then go into the ARC-SWOT modeling tool that we will use to develop the Watershed Water Quality Assessment. Next, I will go into the SWOT model input datasets, followed by model setup, and then we will go into the results and first take a look at the baseline results. Then from there, we will try to implement some best management practices, followed by an economic analysis. The Vermilion Creek watershed is located in northeastern Kansas and covers several counties. The watershed is located within the Huck 8 102 70102 watershed and within the Huck 10 boundaries. This Huck 10 102 7010202 actually defines the boundary of the Vermilion Creek watershed. Again, it covers several counties, starting with Pottawatomie County, which is defined by the purple area, so about 72% of the 150,000 acres of the Vermilion Creek watershed resides in Pottawatomie County. 25% of the Vermilion Creek watershed resides in Nemaha. 1.5% resides in Jackson and in Marshall County. Some elevational information on our watershed is our high point is at 470.19 meters and our low point is at 287.06 meters, with a difference of 183.13 meters. Our total maximum daily loads of pollutants, so we took a look at the total nitrogen, phosphorus, and suspended solids and found that the shapefile that was given to us didn't really have anything recorded in those fields, likely indicating that it wasn't significant. However, fecal coliform bacteria was ranked as quite high in our total maximum daily loads. And this is likely because of the amount of livestock residing in our watershed. So there's quite a few chickens, and then coming in second is swine, and then other types of livestock comes in third, followed by beef, and then dairy cows. The approach taken to model the Vermilion Creek watershed involved the use of the SWOT tool. So what exactly is SWOT? SWOT is an acronym for Soil and Water Assessment Tool, a river basin scale, continuous time, and spatially distributed model. This tool is used to predict the impact of land management practices on water, sediment, agricultural chemical yields in large complex watersheds with varying soils, land use, and management conditions over long periods of time. SWOT will subdivide a watershed, which they call a basin since it's much larger, into subwatersheds, which they call subbasins. Each subwatershed is then subdivided further into hydrologic response units. SWOT simulates a hydrological cycle based on the water balance equation given here. Watershed definition. The Vermilion Creek watershed area was defined by using the USGS stream gauge location. Here are some statistics on this particular stream gauge. The location of this particular stream gauge caused a portion of the watershed to be cropped off towards the south. This still leaves about 90% of the watershed, or about 150 acres, to study. Watershed delineation. The next step in our SWOT model was to take this DEM and feed it into the SWOT model. So starting with our digital elevation model, we worked at a 10-meter resolution, and this particular cropping of the DEM left us with a difference of 183.13 meters. The first step was to delineate our reaches, and this was done with a flow accumulation greater than 150,000 cells. The next step was to define our pour points, and this was done by using the HUC 12 areas. After our subbasins were defined, I then went on to delineate a flow routing diagram. After the watershed was defined, we then went on to land use, soils, and slope for SWOT input. Starting with our land use, we subdivided our 150,000 acres into grassland pastures, which is about 62% of our watershed. 12% was deciduous forest, 10% soybeans, 9% corn, 3% were developed or open space, 1% was classified as other, such as hay or non-alfalfa, and 3% were other types of land uses. Next, we took a look at our soils. And the particular attribute of soils that we paid attention to was the hydrologic soil group. Vermilion Creek watershed area does not have any hydrologic soil group type A. However, most of it is hydrologic soil group D, which consists of about 63% of our watershed. 28% is of type D and 5% is of type B. The third data set we took a look at was slopes. We broke our slopes up into two categories. The first one ranging from 0 to 3%, and the second one was 3% or greater. And we did this because areas with a slope of 3% or greater may qualify for some state or federal funding if they implement best management practices. About 83.5% of the Vermilion Creek watershed area consists of 3% or greater slopes. After we collected these data sets, we then fed them into the SWOT model. The hydrologic response units were then generated. In the Vermilion Creek watershed area, 659 HRUs were generated out of 7 subbasins, 5 state map unit ID soil types, 26 land uses, and 2 slope types. The next data set needed by SWOT was weather station information such as precipitation and temperature. Weather information was collected from the NOAA website and then processed using Visual Basic. The NOAA data typically had missing data in dates, precipitation, and temperature and needed to be filled in. Any dates that were missing needed to be populated with dates, and corresponding dates may have missing precipitation and or missing temperature. If any of these values were missing, the value of -99 had to be entered into these records. Finally, we had to make some assumptions. And these assumptions were related to the land use operations and management. Here we can see some of the assumptions that were made for corn and row crops, sorghum, soybean, winter wheat, and grazing. After we inputted the weather information, we then ran the model. After the model was ran, we then went into calibration. And we did this by creating a hydrograph. So starting with our precipitation input, we also added our uncalibrated, simulated hydrograph information, followed by our stream gauge data, and we found that the error between our uncalibrated hydrograph and our observed was about a -24. We then went on to calibrate the model and was able to get our NSE value to a -0.2. We stopped at this point in time knowing that we had a lot of missing data in our precipitation that could likely offset these values. Other statistical methods such as R-squared and p-bias would likely need to be used at this point in time. Once the model was adequately calibrated, we then took a look at the baseline results. First, we took a look at the total nitrogen results, and we can see that our maximum total nitrogen comes out of subbasin number 6. Next, we took a look at phosphorus, and we can see that phosphorus is low compared to the total nitrogen values. And again, our subbasin number 6 still comes out as being pretty high in nitrogen. Next, we took a look at our total suspended solids, and we find that subbasin number 7 takes the lead in total suspended solids. From here, we determined that our critical subbasin areas would be subbasin number 1, subbasin number 2, and subbasin number 5. We chose these because of their location in the watershed overall. Subbasin 1 and 2 are high in elevation, so we assume that any total suspended solids that drains from these would cascade down the reach and would accumulate in subbasin number 7. We chose subbasin number 5 instead of subbasin number 6 for similar reasons. Our hopes is to try to mitigate some of the total suspended solids before it reaches subbasin number 6 and 7. Next, we took a look at Best Management Practices, or BMP Selection. We developed two scenarios. Our first one, called BMP Scenario 1, involved riparian strips and grass strips. And these ideals are based off the concepts presented in the Best Management Practices to Mitigate Fecal Contamination by Livestock of New Zealand article. In this article, the takeaways were cattle are typically attracted to water, and by deploying riparian strips and grass strips, it creates kind of a natural barrier to keep them away from the water. It also entraps microbes from cattle and other animals being washed downslope towards the stream. In our second scenario, we took a look at a brochure called The Systems of Best Management Practices for Controlling Agricultural Non-Point Source Pollution. And the takeaways in this brochure was that no one single BMP can control a pollutant, and that instead a system of BMPs must be used, such as riparian strips and management operations. And the main ideal is to reduce the travel distance of water-carrying pollutants. In our first BMP scenario, we implemented it in SWOT and took a look at its total pollutants. We can see for total nitrogen, if we take a look at subwatershed, subbasin 1, 2, and 5, that these values are now much lower compared to the other subbasins, where before they were higher. In total phosphorus, we see that these values have also been reduced for subbasin 1, 2, and 5, where we implemented the BMPs. For total suspended solids, we see similar results, where subbasin 1, 2, and 5 are now much lower than subbasins 3, 4, 6, and 7. So our critical areas, subbasin 1, subbasin 2, and subbasin 5, now have lesser or decreased or reduced pollutants compared to our other subbasins. So again, in this implementation scenario, we implemented riparian strips, grass strips, and terracing in subbasins 1, 2, and 5. In BMP scenario number 2, we took a look at a system of BMPs and we implemented them in pasture and agricultural lands. So our total nitrogen has been significantly reduced overall. Our total phosphorus has been dramatically reduced compared to our baseline scenario run. And our total suspended solids is even yet much more improved, especially in subbasin 7. So again, this BMP scenario employed all of the solutions of BMP scenario 1, but we also incorporated some management operations such as contour farming, keeping the residue on the farmlands after harvest time, and no-till. So taking a look at BMP scenario 1 at the total pollutant load reduction, and if we compare it with our baseline, we can see that subbasin 1, 2, and 5, where the BMP strategies were deployed, that the total pollutants are dramatically reduced. So for subbasin 1, 2, and 5, we see the total nitrogen has been reduced by 48%, 39%, and 64% respectively. In subbasins 1, 2, and 5, total phosphorus was reduced by 44, 33, and 56. And then again, for total suspended solids, we see similar reductions at 75, 57, and 94% for subbasins 1, 2, and 5. Taking a look at BMP scenario number 2, total pollutant load reductions, we have for all subbasins, because recall we deployed these BMPs for all pastures and agricultural lands across all subbasins, not just only for subbasins 1, 2, and 5, we see that the total nitrogen load has been reduced by 63%. Total phosphorus has been reduced by 85%, and total suspended solids reduced by 94%. Now if we take a look at BMP scenario 1 and 2 and compare those reductions, we can see that the best management practices scenario 2 has a total reduction of 55% in nitrogen, an 85% reduction in phosphorus, and a 77% reduction in total suspended solids. Total cost of BMPs. So cost to implement. Subbasin 1, 2, and 5 areas were multiplied times the cost of the riparian strips, which was about $150, grass strips, which was also $150, and terracing, which was about $320. and this came out to be pretty close to 30 million. So this is for BMP scenario 1. Now if we took a look at BMP scenario number 2, where we did everything that we did in BMP scenario 1, but we applied it to all of the subbasins that had pastures and agricultural lands, and we included contouring, residue, and no-till, and this came out to be about 77 million. So BMP management practice scenario 2, which has the greatest effect at reducing total pollutants, costs a lot more, $77 million, compared to BMP scenario 1, which also reduced pollutant loads but not as dramatically as BMP scenario 2, but costed $30 million. So residents of the watershed will likely obviously choose the $30 million solution compared to the $77 million solution for cost reasons. So one might conclude after looking at the price tag that BMP scenario 1 is the most practical and feasible solution economically. However, one should consider hidden costs associated with the loss of a healthy ecosystem. Ecosystems provide services that moderate the weather extremes and their impacts, disperse seeds, mitigate drought and floods, protect people from the sun's harmful ultraviolet rays, cycle and move nutrients, protect stream and river channels and coastal shores from erosion, detoxify and decompose waste, control agricultural pests, maintain biodiversity, generate and preserve soil and renew their fertility, contribute to climate stability, purify the air and water, regulate disease-carrying organisms, pollinate crops and natural vegetation. This delicate symbiotic relationship we have with nature is broken when many human activities disrupt, impair, or re-engineer ecosystems every day, including runoff of pesticides, fertilizer, and animal waste, pollution of land, water, and air resources, introduction of non-native species, over-harvesting fisheries, destruction of wetlands, erosion of soils, deforestation, and urban sprawl. Ecosystem services are so fundamental to life that they are easily taken for granted, and so large in scale that it is hard to imagine that human activities could destroy them. Nevertheless, ecosystem services are severely threatened through, first, growth in the scale of human enterprise, population size per capita, consumption, and effects of technologies to produce goods for consumption, and two, a mismatch between short-term needs and long-term societal well-being. So the question then becomes how to sell ecosystem services and their associated long-term benefits and cost savings compared to focusing on the immediate costs of BMPs, which are needed to achieve those long-term ecosystem service benefits. Recall that watershed residents are concerned about the availability and sustainability of resources for current and future generations. In order to sustainably maintain resources for future generations, immediate costs cannot be the only costs assessed in this economic analysis. In conclusion, BMP Scenario 2 is actually the most cost-effective choice to make long-term, considering the integrity of ecosystem services and its ability to serve for future generations.